Hi guys, welcome to Learning Electronics Repair. This is the MultiLOAD project I've been working on, sponsored by PCBWay.com of course, and this is what's called an electronic load. These sort of devices are quite expensive to buy, so I was working on this project based on a previous project I actually found on PCBWay.com to make a load which you can connect to a power source, whether it's a power supply, a power bank, battery, whatever. Put a load on there, and on the final version you'll be able to see the voltage from the power supply loading, the current the load is drawing, and the wattage that is being dissipated. Okay, so the idea of this basically is to test power sources to see if they will operate within their specified ratings. Will they provide the power they say they will, and will they do that over a period of time? So that's the project we have. This actually is being designed to work with USB, USB-C. You can see on here, this little board is what's called a decoy. So this allows the device to control PD USB power supplies. These are the ones that can give various voltage outputs, 5 volts, 9 volts, 12, 19, up to 28 on the latest PD version 3.1, so we can control that from here. You can also connect banana plugs in here, 4mm plugs, so you can connect any sort of power source really to this. And yet it's quite a simple device. The original version was just using one transistor, and it could load up to 35 watts. The idea of this one, it has 4 transistors in parallel, and it should be able to load up to 140 watts. If you watch the previous video, I built the MultiLOAD from the PCB. This is from PCBWay.com. When this is completed, this project, the final version will be available on PCBWay.com. You'll have the Gerber files, the schematics. We're adding the voltage, current and wattage monitoring door to board, so you'll have that as well. Separate schematics, separate little PCB, source code. It'll all be there for you, so you can either buy the boards to make these things, or you can, if you like, play around with the source code. It's all open source. By all means, modify it. And hopefully, of course, in fact, definitely, more heads are better than one. So where did we get up to? Well, I had this working on the previous video, and then I went to get a high powered PD power supply, about 100 watt, and put a higher load on. So originally I had about a 3 amp load, about 15 watts loaded originally. I got the other power supply so we could load about 100 watts, and once I turned the power up, one of the transistors went short circuit. So at the end of that video, I traced it down to be this one. So in this video, we'll replace this transistor, and then I'm going to get the thermal camera as this stands, and we're going to have a look at this. So I won't put such a high load on to blow the transistors again, or even one of them, because I only have 2 left. I've ordered some more. But I want to see at loads this was handling if one of the transistors is getting hotter than the others. In other words, is one of them doing all the work, not being spread evenly? Because that's why I suspect, and why some subscribers also said, as I say, more heads are better than one head. This is what's causing the problem. Okay, so let's prove it, and then let's see how we get around it. So first of all, which transistor went short? Well, at the moment, if we read across the collector emitter, it reads short. Okay, on all of them. How about to the base? That reads open. I'll go to diode mode, and I'll put the positive on the base. Let's see if we can figure out which one is short this way. Well, that reads like a diode junction. But these are all in parallel on the collector emitter, so it doesn't matter which one I go to. In fact, they're short anyway, so it doesn't matter. All I can really test is from the base to either collector or emitter. That is like a diode junction. That reads like a diode junction. And that reads like a diode junction as well. I think that one actually reads slightly higher than the other ones. Yeah, that one reads a little bit higher, so one reads different from the other, so that will be the one we try first, of course. Okay. I only need to disconnect one. Are these still reading short? No. Well, again, they're all in parallel, so if one doesn't read short, the others won't read short either. This one is short, so that one has definitely failed, yeah. So we'll take this one off and replace it with a new one. Okay guys, so I have this connected up, power supply at 5 volts. It's drawing 0.008 of an amp, which is about 0.04 of a watt. And if we just have a look around at the transistors on here, in fact I'll just zoom this a bit better so you can actually see more easily. Yeah, something like that. So you can see one transistor here. There's about 32 degrees. This one similar. This one similar. Just try to get onto the transistor. Yeah, it's there. Similar. And the other one, I'll have to move my hand out of the way, but similar. So all the transistors are fairly similar. Now let me increase the load a little bit. So I now have about an amp, just over an amp, 5 watts, yeah? So you would expect, if this circuit is all balanced up, to each transistor to warm up to about the same amount. Now this one is about 34 degrees. Okay, there you see it. This one here, well, we can see it's warmer, it's gone yellow. 38. This one similar, 32. This one similar. I'll put the macro lens on. Just turn the current down a little bit because I don't want to blow any more transistors up. Let's see if this shows us a bit better. So here we have a transistor, very clear now, 33. Okay. This one 33. This one 33. This one 33. Now I'll turn this up to, yeah, about 1.4 amps. Let's have a look again. So this one is now 36. This one is at 38, 39. So that one is warming up. That one isn't warming up. That one isn't warming up. That one is a little bit, 36. This one, well, you can see this one's at 39 already. Let's turn it up a little bit more. It's about 9 watts now. What do we have? Well, this one's about 35 degrees, 36. Same. 37. And this one's at over 40. So you can see straight away that they're not balanced, okay? Bit more power again. 40, 41. 37. 35. 38. So why is this transistor, and this is the one that blew before, why is this transistor getting hotter than the others? Well, here's the basic circuit. We have an op amp, LM358. This is a dual op amp, and it drives our transistors. So we have 4 resistors here. Okay. These are all 1 kiloohms, 1k, 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 and this goes to the base of each transistor. Collector emitter, the NPN transistors, collector emitter, and then all the collectors are connected together. So these transistors are basically in parallel. Okay, and all of the emitters are also connected together to another resistor. So from here, from here, from here, and from here, we go to a resistor. Just come down one line, that's it. Get them level here, join them up. Okay, so we have that. Here we have a resistor to ground. And this is V in. This is the power supply you want to load, which in our case is anything from 5 volts, probably actually from 3.3 volts up to 30 volts. This resistor is very low value, 0.05 ohms, 50 milliohms. And the LM358 monitors the voltage across here, so the more current that passes through, Ohm's law says V equals current times resistance. Well, the resistance is that. The current is whatever's flowing, depending on how we set the potentiometer, and the voltage is the voltage across here. So the actual circuit monitors this, compares it with a reference voltage, and then the reference voltage is set by our potentiometer, so we can alter the reference voltage, and it balances the two together. So if we dial up for more current, it turns the transistors more on, which pass more current until it balances whatever set on the potentiometer. If we turn the potentiometer down, it then reduces the drive of the transistors until the voltage here drops to a certain point, and then it settles at that again. So basically the potentiometer alters the current. So why is one of our transistors getting hotter than all the others? I mean, they've all got their own base resistor, so you can say, well, the voltage on the base of each one can be different from each other because you all have their own separate resistors, but the emitters are all at the same voltage. And this is where the problem starts. So basically, a transistor has gain, okay? The gain is the ratio of the base emitter current to the collector emitter current. So on a transistor with a gain of 10, if this where you have 1 milliamps flowing here, then coming through the collector here, you would have 10 milliamps, 10 times as much, because the gain is 10. Yeah, guys, I know it's a little bit more complex than that, but from our perspective, it's good enough. If the gain of the transistor is 100, you can work it out even before I write it. For 1 milliamp coming here, we'll have 100 milliamps going down there. Okay? But what if the gain of the transistors is not equal? Because it's not going to be. Because just like any component, there's tolerances. So of all these transistors, one will have the lowest gain, one will have the highest, and the other two will be in between. And the one with the highest gain is the one we need to be concerned about, because if we go to the extreme, yeah, big difference in gain. If these ones here had a gain of 20, okay, 20, 20, 20, and this had a gain of 100. So basically for 1 milliamp flowing into each base, 1 milliamp, so each one's getting the same current flowing in. This transistor will be passing 20 milliamps. This will be passing 20 milliamps. This will be passing 20 milliamps. And this will be passing 100 milliamps, because the gain 20, 20, 20, 100. Okay, within the tolerance of our transistor, it's not going to be as big a difference as that, but there will be some difference. What happens to the one that's passing the most current? Well, it's going to get the warmest. What is voltage times current? We know what voltage is, Vn, let's say it's 5 volts. We know what the current is, so in the case of this one, 5 times 0.1 of an amp, that was now 0.5 watts, and these are all giving 0.1, I think we'll find this actually is. Must be, because they're a fifth of the value of those, okay. At these currents, that's going to get a little bit warmer. At higher currents, it becomes much bigger. Power dissipation. So one transistor will get hotter than the others. Now, bipolar transistors, as opposed to MOSFETs, bipolar transistors have a particular property. And that is effectively, as the transistor gets warmer, it starts to pass more current for the same amount of drive. Yeah, it gets warmer. So because this one's warm, equivalent, the gain of this one increases with temperature. Yeah, I know it's technical, guys, but from the point of view of what we're doing, that's good enough. The gain increases with temperature. Okay, so this one now, for the 1 milliamp base drive, now it has 110 milliamps flowing down through here. The other ones are not much affected because you weren't passing much current to start with. So this one gets a bit hotter again. And when it gets a bit hotter again, the gain increases. So now it's passing for the same 1 milliamp, it's giving 120 milliamps going down here. And that makes it get hotter again. So you can see what's going to happen here. As the transistor gets hotter and hotter and hotter, effectively it's amplifying the base current more and more and more to the point where the transistor burns out. And this is called thermal runaway. Okay? And that is a layman's way of understanding what's happening here, yeah? The rest of you non-laymen, you're welcome to comment because I know you're right, and I'm sure lots of us would like to hear the exact ins and outs, but that's what's happening, okay? So, because of thermal runaway, our transistor that started off a bit warmer than the other suddenly gets a lot warmer than the other. It just commits carried self-immolates, yeah? How do we stop it happening? Well, there's quite a simple way to at least make it much less likely to happen, and that's to put a resistor in here on each of them. Okay, this is the emitter resistor. What happens now, if you think about it, as this transistor starts to conduct more current is flowing through this resistor than there was before. This end of the resistor is connected to all the others. So this end of the resistors all have the same voltage because they're all connected together. Okay. But as we know, Ohm's law, V equals I times R. Assuming the resistance stays the same, in actual fact, as the thing gets warmer, the resistance increases, but that just helps what I'm going to tell you. As this transistor passes more current, the voltage drop across this resistor increases. So if the voltage drop across here is increasing, the voltage drop across the base and emitter must be decreasing. Yeah, so the total voltage base to here stays the same, and that's set by the current flowing by this resistor, by the way. But the voltage here goes up due to V equals IR of that resistor. In fact, as that resistor gets hotter with more current, the resistance also increases, and this has exactly the same effect. This goes up even more. So this voltage here is rising up towards the base voltage. That means the base emitter voltage is getting less. What does that cause to happen? It causes the transistor to turn off more. So this transistor starts to pass less current because the base emitter voltage is decreased. Okay? And that effectively is happening on all of the transistors, and it balances them. by having a slightly higher voltage here than it does on that one and that one and that one, all transistors will effectively handle an equal share of the current. Okay, and that's why we have these resistors. Now, how do we work out what value resistors to put in here? Well, there's two ways. Yeah, there's the correct way and there's the rule of thumb. I'll show you the correct way and then you'll realize why I use the rule of thumb. Okay, let's have a look. Well, here is an example of using transistors in parallel. This is a question somebody asked basically, and they have a similar circuit to ours with all the emitters tied together to ground and individual resistors driving the bases. Okay, they're actually just driving a load where we're effectively making a variable load, but that's the sort of thing we have. And there's some discussion about this, and basically the solution is what I'm showing you. So each transistor has its own base resistor and each one has its own emitter resistor. Okay, and then as often happens on all this sort of side, that we then get a simple equation. Yeah, well, if that's simple, yeah, delta times, well, my maths isn't good enough, guys, really, to do that. Maybe with a spreadsheet I might be able to work it out. And they say in beta may vary the temperature, and you have to know what all these things even stand for. Anyway, yeah, what is beta? Is it better? Who knows? So that's one way to figure out what sort of value resistor should go in the emitter. But there's another way, in my opinion, and it's easier. This method is kind of the rule of thumb method, based on look to see what other people have done. So this is a module out of a scrap amplifier, which I was just salvaging for parts. We can see we have 4 transistors. The big resistors here are the emitter resistors. Okay, and we can have a look to see what these are, and we can see that these are 0.5 ohms on each one. Quite common actually in amplifiers, and this basically is a similar thing to our load. It's sinking a lot of current, or rather it's putting a lot of current through a speaker. Yeah, and if you look at these amplifiers in general, you'll probably find a very common value for this is 0.22 ohms, and that's probably the most common of them. So what should the emitter resistor be? Well, I'm going to go with 0.5 and do some experimentation to see if it works. I could perhaps reduce it to 0.22. Okay, why might I want to reduce it if I can't get enough current sunk by this load? But really, putting these in shouldn't have much effect on the current sinking capability of the load, because all will happen is that because of these resistors, the current flowing through here will be less because there's a resistor there where there wasn't. So this LM358 should just drive the transistors even harder to get back to the voltage it wants across here, the current it wants. So I don't think it'll have any real effect. We'll find out. So that's your emitter resistor rule of thumb. What about the base resistors on here? Well, if you look, so emitter collector base, this is a standard pin out. The base is there, goes to here, which goes to that small resistor there. And this is 4.7 ohms. So roughly 10 times that. In fact, on this I quite would have expected to have 0.47 and 4.7. So the base resistor 10 times what is the emitter resistor. And that ties in with the fact that big power transistors like this probably have a gain of about 10. So that is a very good rule of thumb. Now, if you look on our circuit, in fact I mentioned it to you before, our base resistors are much higher. They're 1 kilo ohm. But I don't think that's going to be a problem. Let me tell you why. Here are our base resistors. Actually, I've just noticed the colour balance isn't good on the camera. That is definitely red to me. That looks almost the same colour as the PCB, but the camera is picking up like brown. So if you think I've actually got 100 ohms in here, no, they're 1K, okay? And there's one for each transistor. The transistors are this one, TIP122. And that is not a normal NPN power transistor, it's a special one. And the reason the TIP122 is special is because it's a Darlington transistor. Yeah, little darling. So, couldn't resist that one, guys, that fun. So, basically, the Darlington transistor internally looks like this. Okay. So this is your emitter, this is your collector, and this is your base. This is the input resistor, okay? There are actually internally in here a diode and a resistor in the base circuit somewhere, but that's basically what it is. So it's two transistors effectively connected in series. And what this does is it effectively multiplies the gain of this by this, okay? Quite often with these Darlington transistors, the gain of this might be 1000, could be up to 2000, something like that, but about 1000, okay, is what you'd expect for this Darlington transistor. That's why if I put a 0.5 ohm on each of these, I'm not going to put a 5 ohm here. Our Darlington transistor has a gain probably 100 times more than a standard single transistor, maybe 200 times more. So you would think actually probably the base resistor should be about 500 ohms, maybe. That'd be my rule of thumb. But I have no problem with it being 1K, and I don't think it'll have any effect on the performance of the circuit. Guys, you know where to respond to that, yeah? So this is my rule of thumb. So I'm thinking 0.5 and 500. In fact, if it doesn't work properly, I'm going to try 500 in here instead of 1K. But I suspect it probably will work properly. And by work properly means I'll still get the same sort of current sinking ability I had before, but all the transistors will be working evenly, or very close to evenly. We won't get one getting hot and burning out. Okay, you know what we need to do now, don't you guys? Let's try it. I've mounted the resistors right next to the transistors on the heatsink. I'd do well to stick them down with a bit of that thermal cement actually, but this is probably the best place for them because as a transistor heats up, it will also heat up the resistor, which will actually help the effect we're trying to achieve. So let's have a look now if all the transistors are taking an equal load. Well, you can see we're not drawing much current at the moment, so they'll all be running cold. So we'll just find where they are. Yeah, one of them's here. Okay. Cold. Because there's almost no power being drawn. So let's actually turn this up a little bit. Well, you can see we have an amp or so, about 6 watts now. Let's see what we get. A little bit hard to see where it is, but the transistor's there. That thing where I'm looking at now. This is the transistor, okay? And we can see that's about 34 degrees. The resistors are actually a little bit warm. Let's have a look. What's this one reading? Again, there's the transistor, about 34. Okay. Another transistor here. This one, about 33. Last one, about 34. Okay, I'll turn the load up a little bit more so we get a bit more of an effect. We're about 2.5 amps now. Let's have a look. So this transistor is at about 37, 38. This one, 37.4. This one, 37.2, 3. This one, 36.7. fact, if we just zoom out, you can actually see 1, 2, 3, 4, they're all about the same. That's up to full 15 watts now, 3.3 amps. And all those transistors are fairly even. We don't see any one particularly hotter than the others. What's this one? Let's have a look. $39 or something. About the same. About the same. About the same. So yeah, you can see there, guys, all those transistors are looking quite happy now at 15 watts. So that basically is why we put emitter resistors into this circuit, okay? The reason we use quite high wattage resistors is because they will be dissipating some power. We can kind of work it out actually. Means let's just see. We'll use a little bit of Ohm's law. We can see they're all even. And I'm quite happy now that the load is actually working correctly. Let's work out then the wattage dissipation on the 4 resistors. So we know they're 0.5 ohms each, and we know the total current is 3.34, say 3.34 amps. So if we divide that by 4, okay, that'll give us the current through each resistor, and we know the value of the resistor, so we can work out the wattage. Let's just do that. Well, we could measure the voltage drop across the resistor. We know the current flowing through it, and watts equals voltage times current. But we don't actually need to measure the voltage across the resistor because we know the value of it. So we can just use Ohm's law. So Ohm's law, VIR. Okay, we want to know the voltage across the resistor. Well, voltage across the resistor is current times resistance, current in amps, resistance in ohms. So what's the current? Well, the total current was 3.34 amps. And assuming, and this will be close enough, especially with the way we had them balanced, we can see the temperatures are all even. So assuming the current is the same on each transistor, then we can take 3.34 amps and divide it by 4 transistors. So 0.835 amps. So the current on each one is 0.835 amps. Okay, so we know that. The resistance, we know what the resistors are. Yes, we could measure them accurately, but they're 0.5 ohms. And they're 0.5 ohms, pretty close. So if we multiply 0.835 by 0.5, we'll get half of that, which is the voltage drop is 0.417, is close enough. Of course, some of you don't like doing it like that, so then you want me to prove I was correct, so I can do it. So 0.835 multiplied by 0.5, you see exactly what I said, okay? Decimal point slightly out, 418. So that is the voltage drop we will find across the resistor. So what? Well, it's the voltage across the resistor times the current flowing through the resistor, okay? How much power are they dissipating? Let's have a look. Well, it's about 0.815 multiplied by 0.418, 0.34 of a watt, and they were cold. This power supply supposedly can handle 140 watts. That's 35 watts per transistor. I'll need a much higher power supply to test that, but we can have a go when we finish the project. So what would these resistors be dissipating if that was the highest load we could handle? Well, again, we can work it out just from what we've got. The current through each transistor would be 7, okay? and the resistance is still 0.5, so V equals IR, which is 7 times 0.5 ohms, 7 amps, well, half of 7, that's 3.5 volts. Okay, 3.5 volts. And the wattage, well, that's voltage times current. So you can see 3 sevens is 21, and half of 7 is 3.5. So about 24.5 watts on each resistor. Now, my resistors, I think, are 10 watt resistors. So this couldn't actually handle that at all. It's going to handle somewhere less than that. Again, just looking at these figures without doing the reverse maths, I can say it's half of that would still be about 12 watts per resistor. I'll just check the rating of these actually. Doesn't say, so I'm going to say they are in actual fact 10 watt resistors. So I was just trying to figure this one out, guys, but I'm not a mathematician yet. So I was trying to work out how to reverse this. I hope there are some mathematicians out there. So if I know the resistor can handle 10 watts and I know it's 0.5 ohms, yeah, how do I work out the maximum current in amps that can flow through my resistor? Because it's not like half. You're thinking, okay, well, if it was half, then it'd be 12.2, but it doesn't work like that, because if I say the current is half, which is half of 7 amps is now 3.5, then the voltage across the resistor will actually change, because it's now 3.5 times amps times 0.5 ohms, which is 1.75 volts, which means then the whole formula changes, yeah. So 3.5 times 1.75, well, it's a lot less than 12, yeah. So there must be a way to work that one out. You can teach me something, guys. Teach me something. How do I work that formula backwards? Yeah. So while I have quite gratuitously passed the buck on that one, I hope you guys like the method I use of the rule of thumb to work out the values of the resistors we should use in our circuit. Quite clearly with the 1K resistors here, it was fine. It wasn't limiting the current that I could load this 5 volt USB power supply because I had some extra resistance here. It was just driving it harder to make up for it. So I think you've definitely learned something. You guys teach me, okay? And I look forward to hearing from you all by the time I publish the next learning electronics repair video. Ciao for now, guys.